We's pumped for some lenses law questions and Faraday's law. Let's do it. I'm going to go through a couple of the trickier ones, starting with number 2. Number 2 is pretty straightforward, but you haven't done any at this point, so let's do it. Remember, our formula is our voltage equals our number of turns, which in this case is 200, times the magnetic field. Flux is, why don't I write it out? Voltage, negative for the Lenz's law, number of turns, times the change in flux. Change in flux is magnetic field times area, or perpendicular areas. BA cos theta would be reasonable as well. And all of that is over time. So we've got 200 turns. I'm taking away the negative because I don't need to figure out direction in this. It's really just a reminder that, hey, coils like things the way they used to be. And then our magnetic field strength is 3.6 times 10 to the minus 4 Teslas. Our area is figured out using this radius. Remember, area of a circle is pi r squared. So pi times 36. And then we will divide that by the time it took to change its area. So we started with it perpendicular to the field, and so the flux is BA, and at the end it's going to 0. So really we want to find the change in flux times our number of loops. This is our change in flux because we're going from this to 0, B times A to 0. So that's our change in flux, and we're dividing by time, which is 0.015. Plug that in your calculator, you're done. Remember, solutions are also available on the Google Classroom if you want the numerical answer. All right, so this next guy, pretty similar, same kind of idea. We got to figure out our change in flux divided by change in time. We do not have to, we will need to figure out the direction of current, but we don't have to do anything fancy. We don't have number of loops or anything. So in this case, our voltage is just BA over T. You might want to make it negative BA, but whatever. Doesn't really matter. We will figure that out later. So it would be just 2.2 times 10 to the minus 2 Teslas for our B. Our area is given to us. It's going from this area to 0. So we will do 2.5 times 10 to the minus 3 all over our time, 0.1. So we're just doing change in flux divided by time. That'll give us our numerical answer, but we also need the direction of the induced current. I recommend using the second right-hand rule I taught you, where for solenoids. So fingers are direction of conventional current through the coils, and your thumb is the direction of the magnetic field. This coil loved it the way it used to be, like it used to have tons of magnetic field lines going through it into the screen. So if you set up your thumb, for you it would probably look like this. Anyway, so from your perspective, this would be going counterclockwise, I believe. So yeah, thumb into the page because that's the direction of the magnetic field, and then fingers curl in the direction of the current through the coil, which would be clockwise in this case. Let's try the next sucker. We've got a square-shaped coil with 100 turns. The only reason I chose this one is because you're looking for magnetic field strength instead of the usual. So it's the same thing, but we're rearranging the formula. So it's still V, or our voltage or EMF, is equal to our number of turns times the magnetic field, which we don't know, times the area, divided by the time it takes to do its thing. Remember, this is change in flux, but again, since it's rotated through 90, then it's going from full flux BA to 0. So it works out great. I guess it's going from 0 to BA. Either way, the magnitude of the magnetic field strength will be the same. So anyway, if we rearrange this sucker, kicking things diagonally across the equal sign, kick this guy up here, these guys down here, we will end up with our voltage times our change in time divided by our number of turns times our area equals our magnetic field strength. And so we just plug it in 0.92 times the time, which is 0.12 seconds, divided by our number of loops, which is 100, and our area, which is 4 times 10 to the minus 3 meters squared. And plug that in, you're done. That's it. Just a little bit of rearranging to solve for B instead of V. It's the big difference, that one. I chose this guy because it's got the direction of the magnetic field getting reversed. And remember, we've done a lot of what matters is the change in flux, but all the previous examples have gone from like BA to 0 or 0 to BA, so the magnitude was the same either way. In this case, it's reversing. So it's kind of like going from, you know how if you go from 5 meters per second north to 0, you've got a change in velocity of 5 meters per second. But if you go from 5 meters per second north to 5 meters per second south, you've got a change in velocity of 10 meters per second south. So that is the kind of thing we're going to have to do here. Only instead of meters per second, we're talking about Tesla meters squared, or Webers, our change in that. So because of this reversed, it's kind of double what you might think. So we set this up aside from that exactly the same as all the others. It's the number of turns times our magnetic field times our area all over the change in time. Keep in mind this is the change in flux. So our change in, if you're going from like 5 up to 5 down, your change in is 10. So our total change in flux will be 2 times B times A. So it'll equal 10 times 2 times 2.7 times 10 to the minus 3 times our area. We've got a diameter too. This is another thing. We have to play with that. So we need the area of a circle with a diameter of 25. Convert that to a radius. Our radius is 12.5. And then we'll just do 12, or pi times 12.5 squared. So 2 times the magnetic field times the area, because it's not just going from full strength to 0, it's going from full strength in one direction to 0 to full strength in the other direction, all in this amount of time. By the way, assuming it's changing uniformly, you could also have said, hey, it went from this to this magnetic flux to 0 in half the time if it's reversing. And so you could get rid of the 2 and make this 0.15 for exactly the same answer. Anyway, that is the gist of how you do it. Careful with this reversed, just with the same idea as finding your change in velocity. If something changes directions, you kind of have to double it. If it reverses and it isn't the same magnitude as before, you can do kind of a final minus initial, but give one of the directions, make one of the directions positive and the other negative. Like flux final minus flux initial is change in flux. All right, then we got this sucker. I just picked it because it gives you Teslas per second, which is our 0.4 Teslas per second is really equal to B over change in time. It's kind of like change in B over time. So we're just going to use this as both variables in our formula. V equals our number of coils times our change in flux, which in this case, it's our magnetic field that's changing, delta B A all over delta T. But all of this is just one thing. So we will just go 25 times our rate of change of the magnetic field, which is just 0.4. That's taking care of both those variables for us. And then times the area, which is just 5 times 10 to the minus 3. And that's that one. All right, last guy. So we've got this square-shaped piece of wire in the magnetic field. It's going from 0.6 Teslas to 0 Teslas in 0.05 seconds as you pull the loop out. The average EMF induced in the loop, I'm just going to leave to you to figure out. It's pretty standard. What I want to do is B and C. Well, actually, I guess... Anyway, so you find your voltage from here, and then we're going to use it to find the current induced in the loop. So we will have a voltage, V equals IR, business. So just reminding you, that still exists. We know it's 12 ohms, so whatever you got from this guy, V coil, I'll call it. So whatever you get from this guy, from your NBA over T, or change in flux over T. Whatever you get from that, put in here, V coil. So your current is just your answer to the first one divided by your resistance, which I believe was 12. And then for the last bit, you want to know what's the direction of electron flow in the loop. I'm going to find conventional current and then just, I'll show you two ways. So this coil here liked things the way they used to be. It's like, I liked it when I had all these electric field lines coming through it, and now you're taking them away. I'm going to fight to keep things the way they used to be. And so if you do your solenoid right-hand rule, you can find direction of conventional current. I guess for you, it'll look like this. So thumb pointing out of the screen, fingers curling in the direction of the coil. So that would be counterclockwise. So the conventional current will be counterclockwise, and therefore your electron flow is opposite to conventional current. So that would be clockwise. So electron flow would be clockwise because you figure out the conventional current is counterclockwise. By the way, you could also use your left-hand rule to figure that out. Same deal. Left-hand rule is for negative charges, electron flow instead of conventional current. So yeah, fingers direction of conventional current, thumb direction of magnetic field. You're good to go. Have a great rest of your day. Thanks for watching.